We are biologically inclined to view motion, right? Our eyes are more drawn to something in motion than to something that's stationary. Would you agree with that? When somebody walks in the door, what's everybody do? Right? Everybody has to turn and look because we see something else moving. Okay, we are biologically inclined to motion. And so we've got to start being able to analyze what that motion is, okay? When an object is in motion, we have to think about it in a different frame of reference than we had before. And we have to start thinking about how is its position changing? How is its velocity or its speed changing? All that kind of stuff. So there are several different ways an object's position can change. The most basic type of motion is straight line motion. That means we're moving forward, backward, side to side, either in the purely X direction or purely Y direction. Okay, when I say horizontal, what's that mean? Flat, right? You have to know that. Horizontal is flat and vertical is up and down. Okay, so if we say straight line motion, that means an object could be moving horizontally or vertically, but not both. Okay, horizontally or vertically, but not both. If you have object that is moving in a circular path, what are some examples of objects that move in circular paths? Kind of. Okay, I would count a merry-go-round. Okay, or carousel, yeah.
Tires on cars.
Yep. Car vehicle tires,
Yo-yo.
A ball, or would that not count because it's like?
Kind of depends. I'm gonna call that an arc motion, okay, or a projectile motion, because those are objects that move through the air both vertically and horizontally, right? Do you understand that path? That motion is kind of like a parabola, right? It's going to move through the air both horizontally and vertically. That's almost any type of athletic game, right? Any type of ball we put into motion typically has an arc pattern, okay? With the exception of like bowling, hopefully, right? Hopefully bowling is like flat. But otherwise, when we kick a ball, throw a ball, whatever we have to do with that ball is moving both horizontally and vertically, right? Theoretically. Last type of motion is called back and forth motion, and that would be an example with anything vibrating. It would be pendulums. Do you know what a pendulum does?
Mm-hmm.
Back and forth, back. Where do we see pendulums? Yeah.
Grandfather clock.
In a clock. Yep. Where else?
An Edgar Allan Poe story.
Okay.
It's like little
The music thing?
Yeah.
Oh, a metronome.
What are those balls that you drop?
Newton's cradle. Back and forth. Good. A swing, right, on the playground. That would be considered a pendulum. Any type of thing that has, we call it simple harmonic motion. That means repetitive motion. Okay, those are all different types. So we're going to start our units with straight line motion and projectile motion or arc motion, being able to look at that. Circular motion is objects that move in a circle but don't spin. So there's a little bit of a difference there, right? Moving in a circle would be the planet's orbit itself, not the spinning on the axes, right? There's a difference between rotational motion and circular motion. Okay, so we'll study rotational motion way later, but circular motion is just circular path. So, okay, straight line motion, blah, blah, blah. It relates to a place and a time. This is the most simple straight line motion you can get. This vehicle moved from point A to point B in some amount of time. We would be able to calculate lots of information about it. How far did it go? How fast? How long did it take? Right? Knowing some information that we need to know. That's about as simple as your motion diagrams could be and maybe need to be, is this line. That's a motion diagram. Okay? There's no need to draw the car, right? I'm not an artist. Okay? I can draw a line though, most of the time. Okay? So A to B, that's pretty much our motion diagram. We have to be able to visualize, right? If I say, okay, this guy's standing on top of some platform, right? He throws a ball off the platform. It goes in the air. It lands on the ground. That's a motion diagram. It gives me a good idea of what happened with my motion. Am I going to win any awards for it? No. But is it going to do what I needed to do? Yeah. And so drawing that motion diagram is going to be really important. Okay? When we draw those motion diagrams or when we start picturing motion, we're going to use a coordinate system that goes with it. And you guys know coordinate systems, right? How many quadrants are in the coordinate systems? 4. Okay, 4 quadrants. I don't need to know quadrant names because I don't care. But you need to know where your coordinate system gets placed, okay? So I'm going to tell you, in our coordinate systems, you get to pick an origin. Okay, and that doesn't mean that you are picking a different spot for 0, 0 to be. I'm just saying you get to pick where you overlay your coordinate system on your motion diagram. So let's reframe that a little bit. If I have the same scenario, right? Guy stands on top of some platform, throws a ball into the air, right? We want to see what happens to that ball. For me, my coordinate system is going to sit here. Oops. Nope, not there. It's going to sit there. Why there? Where's the origin? Where the ball starts. Okay. Now, here's your alternative. Some people put the origin at the ground. Okay. That's not my preference. I will always work my problems to show where is my object going to end up. Okay. And I'm always going to put the origin where the motion started. Okay. So if my object ends up here, what would its x component be? Positive or negative? X component. Right? It moved in the positive x direction, and where did it move in the y direction? Negative. So here, my displacements or my how far my object traveled would have a negative y component and a positive x component. Does that part make sense? Okay, so some people ask the question, how tall was the cliff or whatever. We can still answer that question because if my ball ends up negative 30 meters below where it started, that means that my cliff was 30 meters tall. Right? Do we see how we can reframe that? That's my preference. Okay, so that's how I'll always work problems. You can do it the other way as long as you understand the big picture of what's happening. Okay, so we pick an origin, which is where our 0 point is. I even to this day, right, as long as I've been doing physics, I will still, right, here's my cliff, here's my object, I still draw the origin just like that. Okay, I give myself a little crosshairs so I know there's where my origin is, right? I don't need to draw a big, gigantic coordinate system, but to this day, I draw that little origin so I know there's where my motion is starting from. So it seems like a minor detail, but it is really important, okay? All right, here are a few things that we need to know about objects that move in a straight line. We have two different ways to describe how far something has traveled, okay? There are two definitions for how far something has traveled, and they are very different. They sound similar, but they are very different. Distance is the total amount of length that an object covered. Total amount of length that an object covered. So if I am starting here, okay, and I walk, okay, 3 meters this way, 3 meters back this way. What's my distance?
6 meters.
6 meters. Okay, pretty simple. 6 meters. But what direction did I go?
Back.
Yeah, so can I give a single direction based on distance?
Mm-hmm.
No, not all the time because I went 2 different directions there. So I can't give a direction with distance. Okay, we're going to talk about that in just a second. But I just can't, right? I can go here, 3 meters, here, 1 meter, here, another 3 meters, and here, 1 meter. I've got 3, 3, 1, 1, so I traveled 8 meters. But I can't give a direction that goes with that because I went 1, 2, 3, 4 different directions. It doesn't work. So distance is the amount of length covered. We don't use that number very often. Okay, we don't use that number very often. We're going to use displacement much more often. Okay, and displacement is not how much length is covered, but displacement is how far you ended up from where you started. Okay, can you see the difference there? How far you ended up from where you started. So when I went 3 meters there, 3 meters back, what was my displacement? 0. Right? My displacement was 0. So it looks like I didn't do anything. Okay, it looks like I did nothing. Same when I made the box. I traveled 8 meters, but my displacement was 0. Okay? And so we've got to really start being able to think through that whole process. Okay? And so displacement is like an eagle-eye view of where we are versus where we started. So when we find our displacement, we're taking the shortest path from where we started to where we ended up. Okay? I accidentally wrote equation here, but I mean to say variable. Okay? The variable, the letter we use to represent displacement is x. Okay? The letter we use to represent displacement is x. What would I do? First of all, do you think that this x displacement is my horizontal movement or vertical movement? Horizontal. So what would I call it if I was talking about vertical displacement?
Y.
I would call it y. Okay, so we could go X or Y. Okay, so we know that those variables mean different things. Okay, what do you think I will measure displacement in? What unit would I probably use? Meters. Yep, I'm going to measure it in meters. Not feet, not inches, not miles, not even kilometers, meters. Okay, so to work with all the equations we want to work with eventually, our unit is going to be meters. All right, displacement is what we consider a vector quantity. Have you heard that word before? Vectors. What's it have to have? Love it. Magnitude and direction. Good. Did you guys just learn that in calculus or pre-calc or something?
Despicable me.
Oh, okay. All right, haven't heard that one before. Okay.
And magnitude. Oh yeah.
Okay, wow. No, I didn't. I have never had a class tell me that. Okay, no, I've never seen Despicable Me, I know.
Use it for your next.
It does have to have both magnitude and direction, okay? Do you know what those things mean? Okay. Okay, magnitude is just the number, right? And direction is our cardinal direction, or, so it could be north, south, east, west, or it could be just positive, negative. So you can choose that, okay? So a vector cannot just say 3 meters. Okay, it has to say 3 meters north or 3 meters south or west or whatever it might be. Here's the rule I'll give you for that. If you are given a cardinal direction in your problem, you must include a cardinal direction in your answer. If it just says it moves forward or backward, right, then a positive or negative would suffice. But if it gives you a cardinal direction in your problem, your answer has to be having a cardinal direction. Okay? Distance, on the other hand, we said can't have a direction because it doesn't have, we might go multiple ways, okay? So it has to have a magnitude and a direction. Displacement is one example of a vector quantity. There are several types of vectors. Vectors are just types of measurements, okay? And so other types of vectors are velocity, acceleration, force. Those are all other examples of vectors, which means all of those things also have to have magnitude and direction. But displacement's the first one we learn about. Okay, it has to have magnitude and direction. We represent all vectors with an arrow, okay? All vectors are with an arrow. And so they need to technically be drawn to scale. And so what I mean by that is at least a proportional scale. I don't mean you have to get out a ruler and come up with a scale key and all that kind of stuff. But if we say it moved 10 meters and then we say it moved 2 meters, does that look like it's drawn to scale?
No.
It does not, right? We need to make sure that our vectors, at least in relationship to one another, are drawn to scale. Okay, and that gives us a better idea of what our motion looks like if we can draw to somewhat of a proportional scale. Okay. All right, so vectors are things that have to have magnitude and a direction. A scalar, on the other hand, is something that only has to have a magnitude. That's only a number. It cannot include a direction. And so those are things like distance, time, and temperature. Right, distance, time, and temperature. There are other versions of scalars, like speed, too. I didn't include that on there. But we don't use scalars a whole lot. Okay, scalars don't have a lot of use for us. We have focused mainly on vector quantities. Okay? So let's talk about, let's go back to vectors now. Okay, vectors, when we look at vectors, we can add them graphically or algebraically. We can add vectors 2 different ways. And so what I mean when I say add vectors is if I say this guy walked east, then north, then east again, then south, then west, then south, and whatever he did. This would be an example of adding them graphically. I would be able to find out how far is he going to end up from where he started. Right? I'm going to be able to do the math and draw it graphically to figure out where he's ending up. That's what I mean when I say adding our vectors graphically. We're going to put them on a visual and be able to see what they look like. Okay, we're also going to be able to add them algebraically, but we'll get to that a little bit later, okay? So when we add them graphically, we're going to draw them to scale, right? We said a proportional scale. We are going to use what's called the tail to tip method. And this seems really minor, but it's really, really important, okay? What this method means is that here's my origin, right? You see how I draw the little crosshairs? That's my origin. That's where I'm starting. Let's say this guy goes 10 meters east. he also goes 3 meters south. Okay, the tail to tip method looks like this. 10 meters east and 3 meters south. So now, can I figure out a straight line path from the origin to where he ended up? I can draw it like this, right? I can figure out how far is he from where he started. Here's what some people tend to do. They will say, okay, he went 10 meters east and 3 meters south. And so then, does it take me anywhere from my origin? Is that hypotenuse value going to be the same as that one? Yeah, it's the same triangle, but here's the problem. I don't have a direction to go with it, right? Because I don't know, am I finding this angle? Am I finding this angle? I don't have anywhere from my origin that it's leading me, right? This is not taking me anywhere. So that's really important. That's why the tail to tip method is so important. And so what that means is that we go from the tip of one vector, we add on the tail of the other when we're adding our vectors graphically. Okay, so let's draw it one more time. Here's the origin. The first vector goes on. The second one goes directly after. Okay, the tail of the second touches the tip of the first. Okay, are we comfortable with that? It seems like such a minor detail, but I promise it's going to make a huge difference. Okay? All right, tail is always the starting point, and the tip is always like where the arrowhead is, right? That seems simple enough. When we draw that diagram, we get what's called a resultant vector, okay? And on my last one I drew here, all right, let's go back to that, 10 and 3. This purple vector right here is what's called our resultant vector. And it is the graphical sum of all of my vectors on my diagram. Okay, it's called the resultant vector. It always gets drawn from the origin to the tip of the last vector. Okay, it is from the origin to the tip of the last vector. So it is, it's the graphical sum, right? It's the weighted average. It's the whatever you want to call it, right? It's the final bird's eye view from our starting point to our ending point. That would be called our resultant vector.
Wait, I have a question.
Uh-huh.
In order to
Okay, this is a really simple, just purely horizontal example. Okay, we're going to start at the origin. The runner starts here. You can draw this out as you're going. Okay, it runs forward 2 meters. Which direction do we consider to be the forward direction? To the right, right? And so on a coordinate system, positive, positive, negative, negative. Do we feel comfortable with cardinal directions? North, east, south, and west. Okay, we've got to feel good about cardinal directions. We won't really need that for this particular one, but okay. Starts at the origin, runs forward 2 meters. We're going to draw it with an arrow. Then they run backward 6 meters. Do I start over at the origin? No, I start right from where I'm from. So I'm going to go backwards 6. So 1, 2, 3, 4, 5, 6. And technically I should draw it right on top, but I want you to be able to see the different vectors. So realistically, I should draw it right on top like that, but I want you to see them. Then we're going to go forward 4 meters. 1, 2, 3, 4. I happen to be back at where I started. Then we're going to go forward 5 meters. 1, 2, 3, 4, 5. So my ending point is here. Okay, and so if I draw my resultant vector, it's going to go from the origin to the tip of the last vector. So the blue one happens to be my resultant vector. Okay, it happens to be the same as that one, but that's coincidental. Okay, so my resultant vector will be that my runner ends up positive 5 meters. My displacement here is positive 5 meters. Because from where I started to where I ended up is 5 meters in the positive direction. What would my total distance be? 17 meters is distance, but my displacement is plus 5 meters. Yeah.
Can we also do like...
Okay, any other questions there? Very simple when it's just purely horizontal, right? Let's move on to one that's a little bit more complex. Not a lot, but a little. This one says they move 11 kilometers north, then 11 kilometers east. Okay, I'm going to change one thing because, I just feel like it. Let's make this a 9. I don't want it to be a 45-degree triangle. I want it to be different. So I want it to go 11 kilometers north and 9 kilometers east. So let's draw out what that looks like. I'm going to count each of those as 2 meters. So 2, 4, 6, 8, 10, 11. Ooh, I barely got there. Okay. 11 kilometers east, north. And then where do I go? Left or right? To the right, right? Do I do like this? That? No, because that's not tail to tip, right? We have to go here. 2, 4, 6, 8, 9 kilometers. So I'm going to write 9 and 11. So now I'm going to draw my resultant vector, which goes from where? Origin to the tip of the last vector. So my goal here is to find what's this guy's displacement, which means I need to find out exactly what this length is. And I also need to find out what direction he left the origin at. So I need to find that angle that goes with it. Okay, so let's go ahead and find this length right there. What am I going to use to find that? Pythagorean theorem. Okay, so I'm going to go 11 squared, 9 squared, take the square root of that. I got about 14.2 kilometers, right? If I'm thinking about sig figs, what's it really going to be? 14 kilometers, right? This is a whole number. I'm just going to round that to a whole number. I'm not going to make you round it farther than that. Okay, 14 kilometers. And so if I say, okay, his displacement's 14 kilometers, is that enough information? No, not good enough. Can I just say his 14 kilometers northeast? No, because that could mean he could leave any of these directions, right? I need to find out how he gets exactly to there, okay? And so I need to find the angle that touches the origin, okay? And so the method that I use, could you technically use any trig function here, sine, cosine, or tangent to find? Because I have all sides of my triangle. But here's what I like to do. I like to use tangent because these are my known sides. This was a calculated side. So if I had accidentally calculated my hypotenuse wrong, then now I calculate my angle wrong as well, right? So my preference is that we use tangent to help solve for my angle. On your calculator, you need to be in degrees all the time in this class. I know it. So sorry. Maybe I'll write a little note up on the board. Always degrees, okay? This is degrees, so you need to go to mode. Make sure that degrees is darkened. So if you're in calculus or pre-calc, you might have to make that change when you come back and forth. But we need degrees to be darkened, okay? So we're going to use, what happens when you have to solve for the angle? What do you have to do especially in your calculator? When you're solving for the angle, what do you have to do in your calculator? I have to go second tangent. So inverse of tangent, opposite over adjacent. Okay, when I solve for the angle using a trig function, I have to use the second, okay, or the inverse. So second tangent of 9 over 11 gives me 39.3 degrees. Okay, run that in your calculator and make sure you get that same answer. 39.3 degrees. Yes? No? If you're not getting that, I want you to tell me. That way I can make sure that we can run that correctly in our calculator, because that's super important. I got about 39.3. Because that's just the rule when we solve for the angle using a trig function. If we were just going to solve for a side, then we would go tangent of theta equals whatever. But right, opposite and adjacent.
I forget all of this.
It'll come rushing back, telling you.
Nope.
Okay, our answer is not yet complete. Not yet complete. It's close, but it's not yet. So right now my displacement, 14 kilometers at 39.3 degrees, what? Just north. No? North of what? Okay, you're going to go, it's going to be blank of blank. East of south. West of north. What's it going to be? Right? Where's my angle? Right here. Tell me, let's answer this question. Here's how I teach this one. What axes is it touching? What axes is that angle touching? North, east, south, or west? It's touching the north axes. And then does that triangle swing east of north or west of north?
East of north.
It swings east of north. So there is my question. Because 39 degrees north of east would put me there, right? Or a little different. So you have to give a super, super exact direction with these displacements. Okay, so we'll always have 39.3 degrees east of north, okay? Had we drawn, let me make this clarification. Had we drawn our vector east first and then north, wouldn't we get to the same final destination? Yeah, we would, right? If we go east 9, then 11 north, we would get to the exact same final destination. And this distance would still be the same, right? That hypotenuse would be the same. But what would be different? The angle would be different. It would be complementary. It would add up to 90 with this guy, right?
Yeah.
So really, if I was going to do this, right, 11 and 9, I'd go second tangent of 11 over 9, and I would get 50.7 degrees north of east. Both of them are acceptable answers because they both take us to exactly our ending point. So you can add vectors in any order. It doesn't matter the order in which you draw them because it's going to get us to our final destination the same way. So either of those answers would be acceptable. 39 east of north or 50.7 north of east.
Even if it says then?
What'd you say?
You say like...
Yeah, that's right. Even if it says then, you can still add them in any order you want to. You cannot mix and match, though. I could not say 39 north of east, right? Because that would be like there, right? It would not be the same final destination. So when we find those angles, we've got to be super, super specific about it. Okay, so with the way we find an angle, let's look at it again. Let's say I have an angle that's right here. Okay, what angle is that? What of what? South of west, right? Because we figure out what axes is it touching. It's touching the west, right? It's only going to be touching one of the axes. It's touching the west, then you decide, does it swing north of west or south of west? And so our answer is south of west. Okay, does that make sense for everybody? Yep, this guy right here means change in. Change in. And so what's another way to describe that change in? What minus what? Yep, x2 minus x1, or we will say it in this final minus initial. Final minus initial. So here's realistically, are we ever going to get a starting time and a final time, or are we going to say it took 8 seconds? We're probably just going to say it took 8 seconds. So realistically, that is getting written delta x over just t. Okay, I don't write out a final and an initial time, right? It's just t for me. Okay, so that's really up to you. Okay, if you wanted to write it out to say x final minus x initial, you could, but I think that is wasted space because you should know what delta means, right? We should feel comfortable with that. We're going to see it often. Delta t. So if you want to write velocity equals delta x over t on your equation sheet, you are welcome to do so. Okay, that is the first equation you'll get. It's not one we use super often going down the road because it's pretty rudimentary, but it serves its purpose, right? The only time that equation is applicable is when something is moving at a constant speed. Okay, so we got our cruise control set. All right, velocity is a vector quantity, which means it has to have what? Magnitude and direction. Magnitude and direction, okay? What would it mean for me to have a negative velocity? I'm going backward, okay? It could mean I'm going backward, or it could mean I'm going downward, right? Downward. It could mean backward or downward. So it means we're moving in the negative direction. Does the negative tell me anything about the number value? Can I move so slowly that I'm moving in the negative speed? No, right? I can't move slower than 0. So -1 doesn't mean that I'm moving so slow I'm moving lower than 0, right? It means that I'm moving 1 meter per second in the negative direction. So we consider west and south negative direction. So on my cardinal direction system, positive, positive, negative, negative. Okay, so west and south are negative coordinates. Okay? We measure velocity in meters per second, okay? Or any sort of length divided by time, but velocity is typically meters per second. That's the goal, okay? The reason for that is when we start dealing with gravity and acceleration, that unit is meters per second squared. And so we need those to be consistent. All right, let's try it. A car travels with a velocity of 50 meters per second east for 2 minutes. They turn south and travel 30 meters per second for 2 minutes. What was the total distance traveled? Total distance traveled. Can I solve both of these problems in one equation? Did they move at constant speed for that entire trip? No, so I have to break it into the two segments that they were moving at constant speed. So I'm going 50 meters per second east for 2 minutes. Then I'm going to reevaluate this 30 meters per second for 2 minutes. Do we see any red flags here with our units? I do, right? We can't say meters per second is distance over time. This has to be in seconds, and that has to be in meters, right? If my velocity is measured in meters per second, my distance is meters, my time has to be seconds. Okay, so for the first portion of my trip, it says I'm traveling 50 meters per second. I'm solving for my distance or my displacement, and my time is not 2 minutes, it's what? 120 seconds. Okay, to solve for x, all I'm going to do there is do what? Multiply or divide. Multiply, good. So 120 times 5. You'd think I could do that in my head, but I didn't. 600 meters what? Oh, I only took it times 5. Okay, times 50 maybe is going to give me 6,000, not 600, sorry. Okay, 6,000 meters east. Okay, are we comfortable with that? Pretty simple. 50 meters every second for 120 seconds. Second leg of my trip was 30 meters per second equals x over 120 seconds. So 30 times 120 gives me 3,600 meters. And what was my direction there? South. If I'm just asking for distance, do I have to include a direction? No, I don't, right? Distance means no direction. So what's my distance covered? How would I find that? I'm just going to add them together. So 9,600 meters. And can I put a direction on that? I can't do it because I went 2 different directions. Okay? But what does the next question ask? I'm not going to click through it because it's going to take my writing away. But what's my next question ask? It asks for what is my displacement. And so how are those things different? Right? I went east 6,000. So I'm going to draw out my motion diagram here. And then I went south 3,600. And so my displacement has to be that right there. What's that blue vector called? A what? Resultant vector. It is the hypotenuse, you're right. It's the resultant vector. And so to find my displacement, I need both the magnitude and the direction, right? I need the hypotenuse and the angle. Am I moving too fast or are we doing okay? Okay, so let's go ahead and solve for that hypotenuse and that angle. Yeah, we do. Yep, because displacement has to have an exact direction. Okay, so I rounded it up to 7,000 meters based on our sig figs that we started with, right? Everything was a whole number before that, and I came out 6,997. So I think that's worth a round, okay? Am I going to be mad if you put the exact number? No, I don't care, okay? I got about 31 degrees when I ran second tangent. Second tangent of opposite over adjacent. And then what's my cardinal directions that go on there? South of east. Very good. Another acceptable answer would have been 59 degrees east of south. Okay, an alternate acceptable answer. You will never have to have both of those. I'm just telling you either one is correct. That would have been the case had I drawn my vectors south first and then east. Okay, which would have been acceptable also. All right, let's try the next one here. We need to drive 40 kilometers east in 32 minutes. What will my velocity be in meters per second and kilometers per hour? I want you to try this one on your own. Try this one on your own. And then we're going to call it, after this slide. I think I want to talk about one more thing, but that's it. Speed has no direction, and it's only a magnitude. So speed cannot be negative, right? If we're asking about what is an object's speed, it's just the scalar quantity. So remember, in physics, the negative just indicates direction for us. It has nothing to do with the numerical value. I can't go so slow, I'm going lower than 0, right? Velocity can be negative, it indicates direction. So I'm not going to go actually even through these next 2 slides. We already did this problem. If I asked what was the average speed, I would use its distance over time. And if I was finding average velocity, I would use displacement over time. That's the only difference. Okay, speed is distance and velocity is displacement. Okay, that's really it. Okay, then this last one says they run the 100-meter dash in 12:2. What was her velocity? That's just a simple calculation of distance divided by time, or displacement divided by time. Okay, I'm going to stop us there, and I'm going to set you apart some time for your homework.